Hello, welcome to class. This is the second chapter of Sensation and Perception, and here we're talking about research methodology. So, basic questions, techniques, and research methods used by researchers to discover how the human sensory systems work. We're going to get into all of that, but first, all of the information I'm talking about I have pulled from this textbook here, and from lectures with Dr. Hasse at Shippensburg University. I'd also like to make clear that I am no expert, okay? This is just my stand-up comedy routine. This is for jokes, this is for fun. We're here to have fun, right? So with all of that said, and without further ado, let's get right into it. The study of human sensory systems starts with psychophysics. Okay, psychophysics is the study of the relation between physical stimuli and perception events. Psychophysical scale, then, is a scale on which people rate their psychological experiences as a function of the level of a physical stimulus. Psychophysical methods involve presenting a carefully controlled stimulus to a participant and asking a question directly of that participant that allows the answer to be quantified, or basically turned into a number. So I'm going to show you something, and I'm going to ask you, hey, in numbers terms, how much of that thing is there? That's kind of like what this method's all about. So, sensation and perception methods, right? The measures and methods of psychophysics help us determine the capabilities and limits of our senses. Knowing our capabilities helps with solving practical problems, like improving vision and hearing. Some methods can even give us insight into our mind and our decision-making process. For example, signal detection theory involves a lot of psychology, and it tells us a lot about how we make decisions based on what we see. Of course, like all sciences, we are trying to measure what we see. So let's talk absolute threshold. The most basic concept in sensation and perception is the absolute threshold. It is the minimum energy required to detect a stimulus 50% of the time. So half the time you see it, half the time you don't. This concept has been around for a long time, but of course the definition is not perfect. Absolute threshold is the smallest amount of a stimulus necessary to allow an observer to detect its presence. And technically, again, it is the 50% correct detection rate, so half and half. This means that if a dim light was shown 10 times, a person may report seeing it about 5. Weak stimuli. So things that are hard to hear, things that are hard to see, hard to perceive. Think of when you had your hearing tested, and sometimes you weren't even sure if you actually heard a sound. And of course there are ways to measure the absolute threshold. One of them is with the method of limits. The method of limits goes like this. Stimuli are presented on a gradual scale, and participants must judge the stimuli along a certain property that goes either up or down. Basically, you present a stimulus, like a bright light, in a sequence of ascending and descending steps. So, ascending means the light gets brighter, and descending means the light gets dimmer. The procedure involves something very systematic, and because of that, the researcher may alternate the ascension and descension of the stimulus. And again, just going over these different series, ascending series is a series in which a stimulus gets increasingly larger along a physical dimension. A descending series is a series in which a stimulus gets increasingly smaller along a physical dimension. The crossover point is the point at which a person changes from detecting to not detecting a stimulus, or vice versa. And lastly here, the 2-point touch threshold is the minimum distance at which 2 touches are perceived as 2 touches and not 1. More on the method of limits. That's a segue. The absolute threshold is said to be the average of the crossover points. One of the concerns with this method is that participants may say that they see stimuli when really they may not actually. The method of limits relies too much on participants' self-report, and because of that, it may not be the best method. The method of limits is often used to determine both absolute and difference thresholds. So let me throw some more definitions at you. The absolute threshold, again, is the smallest amount of stimulus necessary to allow an observer to detect its presence. But then, the difference threshold, or just noticeable difference, JND, is the smallest difference between two stimuli that can be reliably detected. So take a step back and let me give you an example of the method of limits, just real quick. Imagine a lineup of light bulbs in which each one going this way gets a little bit dimmer, right? That's kind of what we're testing out here. So at what point do you stop noticing that there's anything there? The method of limits produces a table of responses, and then the threshold is estimated. When it comes to generating this table, the participant must decide if a stimulus is present at a number of different levels of intensity. The stimulus is increased in even trials and decreased in odd trials. A Y indicates that the participant detects the stimulus, and an N indicates that the participant does not detect the stimulus. The estimate of the threshold is considered to be the mean crossover point. Oh, and fun fact, the absolute threshold for vision is a candle 30 miles away on a dark night. The absolute threshold for hearing is a ticking watch 20 feet away in an otherwise silent location. With taste, the absolute threshold is a teaspoon of sugar in 2 gallons of water. And smell, absolute threshold for smell is a drop of perfume in 3 rooms. Wow. So now let's talk about the method of constant stimuli. Okay, in the method of constant stimuli, the threshold is determined by presenting the observer with a set of stimuli, right? Some of which are above the threshold, and some of which are below it. The stimuli are presented in random order. In other words, the method of constant stimuli presents stimuli in random intensity orders across test trials. The method of constant stimuli is an improvement from the method of limits because of its randomization. For example, running through a series of 60 trials with varying levels of intensity, the first one may be a level 15, and the next one may be a level 3, and then a level 7. The intensity is random. Then we want to find the intensity where the participants said yes 50% of the time, because that indicates that the stimuli was detectable 50% of the time. Now, the graph on the right, red circle, I hope you're looking at your notes, is what the result usually looks like, while the figure on the left is not what it would usually look like. So again, the method of constant stimuli is an improvement from the method of limits. However, people do still differ in their willingness to say yes or no. So again, participants' self-reporting makes things complicated. And you know we couldn't just stop there. We also got to talk about the method of adjustment. In the method of adjustment, the observer, and not the researcher, controls the level of the stimulus and adjusts it to be at the perceptual threshold. The observer does so by increasing or decreasing the level of the stimulus until it feels as if it is just at the detectable level. So imagine there's like a bright light in front of me, and I've got my little knob here, and I'm going to twist and turn that knob until the light is just barely detectable. And the key here with the method of adjustment is that I, the observer, and not the researcher standing over there in that corner, controls this. It's in my hands. Typically, the observer will continuously adjust the knob to control the level of stimulus. This is an intuitive measure for most participants because it mirrors many normal activities. I mean, just think about how many times you adjust knobs, radio, right? Stovetop. Now, when it comes to the advantage here, the method of adjustment can quickly yield a threshold for each participant. However, the disadvantage here is that the method of adjustment leads to great variance from one participant to the next between successive trials for each participant. So, TLDR, the method of adjustment is a quicker, more informal way to estimate the absolute threshold. The observer, instead of the experimenter, controls the level of the stimulus intensity to determine the threshold. Note: the method of adjustment is very useful for matching one stimulus to another to determine the point of subjective equilibrium, or PSE. What is that? Well, I'm glad you asked, because the PSE designates the settings of two stimuli at which the observer experiences them as identical. For example, we, the experimenters, may present some bright stimulus to our participant. The participant would then have to adjust another stimulus to be equally as bright as the first one. Ergo, subjective equality. Closely related to the concept of threshold is the concept of sensitivity. Sensitivity is the ability to perceive a particular stimulus. Now, sensitivity is inversely related to threshold. As the threshold goes down, the observer seems to be more sensitive, and vice versa. So, threshold goes down, observer is more sensitive. Observer is less sensitive, threshold goes up. So lower thresholds mean higher sensitivity. Note, okay, threshold refers to the ability to perceive a stimulus at smaller and smaller levels of that quantity. So a person who can smell smaller amounts of perfume in the air is more sensitive than someone who cannot smell those amounts. Ooh, and fun fact, sensitivity may vary across situations. For example, you are more sensitive to light after stepping out of a dark room. Okay, so all of the methods that we've talked about so far have a number of problems that we should probably discuss now. Classical methods have issues concerning whether a person's response is reliable. Also, a participant's response can be biased, right? They may be too eager to say yes when actually they mean no, or they may be biased to say no even if the answer is yes. And of course, this does not inform the research very well. The other issue is that the absolute threshold is a statistical concept. It is just the 50% point. This concept actually comes up in neuroscience when considering whether a neuron has a threshold, which would be the point at which a neuron fires. TLDR, the absolute threshold is a statistical concept, and a participant's response can be biased. Also, quick note, when I talk about classical methods, right, classical methods include the method of limits, the method of constant stimuli, and the method of adjustment. So the three that we've talked about so far, those are classical methods. So what are some ways that we can improve these? Well, you know we have them. Catch trials and forced choice. All right, here we go. One of the problems that comes up with traditional methods of limits, constant stimuli, and adjustment is that the participant may be misinforming the experimenter about perceptual experience. Now, whether they do this willingly or unwillingly does not matter. It's still fake news. So one technique to counter this misinformation is to use catch trials. A catch trial is a trial in which the stimulus is not presented. It is easy to insert these catch trials as checks on the participant's accuracy and honesty. So in catch trials, the correct answer is always no. No, I didn't hear it. No, I didn't see it, etc. To this point, if a participant reliably says that they saw a stimulus in a catch trial, when the answer is of course supposed to be no, then we can dismiss that participant as an unreliable observer. And another method to counter false reporting is the forced choice method. The forced choice method is a psychophysical method in which a participant is required to report when or where a stimulus occurs instead of whether it was perceived. So instead of determining whether a light was present or not, the participant must decide instead if a light was present in one location or another. On that note, I want to stress that forced choice does not need to have catch trials, because the observer cannot simply say yes in every trial, regardless of the presence of a stimulus in that trial. Forced choice also allows the determination of thresholds, because if a stimulus cannot be detected, performance will be at chance, which is 50% if there are only two choices. Threshold can be determined by finding a level of performance that is significantly above chance. Okay, so TLDR, catch trials and forced choice can reduce bias in threshold measurement tasks. I'm having fun. Are you having fun? I'm having fun. Now let's get into the method of magnitude estimation. Magnitude estimation is a psychophysical method in which participants judge and assign numerical estimates to the perceived strength of a stimulus. And this was developed by a guy named S.S. Stevens. Now, magnitude estimation usually works like this. An experimenter presents a standard tone and assigns it a particular loudness value. Then the participant must judge subsequent tones and give them numerical values in comparison with the standard. So if the participant thinks that this new tone is twice as loud as the standard, then they assign it a number twice as large as the standard. So if I give you a standard of 5 and you hear something really loud and you think it's a 10, well then you better assign it a 10. Magnitude estimation is concerned with the full range of perception instead of just threshold. Magnitude estimation is similar to classical methods because it does investigate how sensitive we are. But magnitude estimation lets us understand the relation between the stimulus and the psychological judgment. There are 3 response patterns in magnitude estimation. One of them is a linear response. This is just the straight line. In a direct way, the physical intensity of the line increases with judgment going in a straight line. So, as the intensity increases, so too does the person's judgment of that intensity. It's just whew. The second is response compression. Okay, as we increase the physical intensity of brightness, eventually the person's judgment will flatten as they no longer see the increasing light as being anything significant. So in this case, the intensity continues to go up, but at a certain point, the person's judgment really starts to taper off because they're not really noticing anything getting any brighter, hence response compression. Getting a little bit more into the compression piece here, with brightness, the person's judgment will flatten out. Their response is compressed, hence the name. So we'll see a curve start out kind of like this, and then eventually it'll kind of taper off because it's like, I'm not really seeing anything here. But then the third one is the fun one. Response expansion is where judgment will first increase relatively slowly, but then as the intensity increases, judgment will suddenly go way up. The perceived intensity is quickly expanding even with relatively small increases in intensity. So this line is kind of slow, but then suddenly it goes whew. You see this a lot with electric shock because the first few shocks may be relatively mild, but then at a certain point you start hitting pain, and when you hit pain, you go. So to put this another way, response compression goes like this. As the strength of a stimulus increases, so does the perceptual response. But the perceptual response does not increase by as much as the stimulus increases. And then with response expansion, as the strength of a stimulus increases, the perceptual response increases even more. And of course, there's a lot of math with this, and I mean, who doesn't love math? My man Stevens illustrated a psychophysical law for magnitude estimation. Absolute tryhard. Stevens' power law is a mathematical formula that describes the relationship between stimulus intensity and our perception. Okay? This accounts for both response compression and response expansion. The formula goes like this. It's like P equals CI exponent value B. P is a person's judgment. Okay, it is the perceived magnitude of a stimulus. So, for example, the number that a person gives based on their own judgment. That's P. I is the actual intensity of the stimulus. So, this would be what the sound actually sounds like, or how bright the light actually is. This isn't what anyone judges it to be. I is just what it actually is. It is the actual intensity. And note, do not worry about C, okay? C is just concerning how stimuli are measured. So it's just like the scaling constant. But importantly, okay, B, this is the exponent. B represents the power that is being raised to in the equation. So the exponent essentially tells us how many zeros follow the number as it changes. At the simplest level, our perception is a function of the physical intensity of the stimulus. But again, this formula accounts for response compression and response prevention. Response compression is caused by the exponent value being less than 1, whereas response expansion is caused by the exponent being greater than 1. Note, importantly, okay, we will not be tested on the formula, okay? You don't need to worry about memorizing all of that. But you should know how exponents affect the relationship. So let me run through this again, okay? Linear response means an exponent is somewhere around a value of 1, right? Linear response, just a straight line, means that the exponent is right around 1. Response compression, that is an exponent of less than 1. And response expansion, that is an exponent greater than 1. So again, you don't need to memorize everything in the formula. You just need to know roughly what the exponent values mean in terms of response. Okay, let's talk about signal detection theory. Signal detection theory is the theory that in every sensory detection or discrimination, there is both sensory sensitivity to the stimulus and a criterion used to make a cognitive decision. Oh, fun fact here. Signal detection theory also overcomes some of the problems with those classical methods that we talked about previously. But back on track. In signal detection analysis, there are some terms that we gotta be familiar with. Those include false alarm, miss, correct rejection, and hit. So let's run through them now. A false alarm is an error that occurs when a non-signal is mistaken for the target signal. A miss is an error that occurs when an incoming signal is not detected. Correct rejection occurs when a non-signal is dismissed as not being present. And lastly here, a hit occurs when a signal is detected when the signal is actually present. Now, I know those were very bare bones definitions, so let's get a little bit more into it. There are 4 possible outcomes on every signal detection analysis trial. For one, if the dot is present and the person says, yes, there is a dot present, that is a hit. 2, if the dot is present but the person says, no, there's no dot, then it is a miss. They have missed it. 3, if the dot is not present but the person says, hey, I see a dot, then that is a false alarm. I'm sorry, there is no dot, also known as a false positive. And finally here, if the dot is not present and the person correctly says, there is no dot, then they have made a correct rejection. I don't want it. Fun fact, a criterion is a bias that can affect the rate of hits and false alarms. So basically, criterion is just differing judgment on the basis of situation. Signal detection theory uses statistical assumptions to measure sensitivity and bias. And here we're talking about normal distributions, also known as the bell-shaped curve. The assumption goes like this. If we do a signal detection analysis, we say that one of 2 things will occur on every trial. Either there will be noise alone or a signal plus noise. The noise alone is just white fuzz with no signal mixed in, right? Whereas signal plus noise is a trial wherein a signal is thrown in amidst all of the white fuzz. When we put this into a normal distribution, we see that there is a sort of dividing line, and that line relates to the person's response as it separates the yes responses from the no responses. We assume that the line is the person's decision. It is basically the fence at which you will fall on either side of based on your yes or no response. If strength is greater than the line, then we can expect a yes response. But if strength is weaker than the line, then we can expect a no response. The curves are representations of the normal distribution, as taught in statistics. The curve on the left represents the distribution of noise, right? Trials where no stimulus is present. And the curve on the right represents trials where the stimulus was present. Most of the time, we will perceive these stimuli. Oh, but I'm not done. When it comes to signal detection theory, there is something important to remember. Sensitivity, right? Sensitivity is the ease or difficulty with which the observer can distinguish the signal from the noise. And let me give you an example of this. Let's say that the noise is just the shower, right? So shower water running down, that's noise. And the signal is the ringtone on your phone, right? So if we have a trial that is noise alone, it's just the shower running without your phone ring going off. But if we have signal plus noise, then amidst the noise of the shower, you will at some point be able to hear, hopefully, your ringtone. Now, as sensitivity decreases, we see more false alarms and more misses occurring. But then, as sensitivity increases, the observer makes more hits and correct rejections. So, as the person becomes less sensitive, they make more mistakes. But as the person becomes more sensitive, they make fewer errors and more correct responses, those being hits and correct rejections. Okay, that was a lot, so TLDR. Sensitivity is the ability to distinguish a noise from an actual signal. For example, the difference between random noise and some clunking sound in your car that you should probably get checked out. Signal detection theory provides us with two stats that are based on some of the possible outcomes. One of them deals with sensitivity. This is called D prime. The other one deals with bias. This is the criterion, or C. Let's start with D prime. D prime is a mathematical measure of sensitivity. You can determine D prime if you know the relation of hits to false alarms. So, in other words, D prime is sensitivity. So, how well does this person do at detecting the signal versus detecting noise? Going back to that normal distribution with the two humps, okay, D prime is the separation between the two curves. D prime is equal to the difference between the two means, which is the extent to which the curves are separated. So, as the difference between the two means increases, D prime gets bigger. Note, okay, Cohen's D gives you the standardized difference between two means. So that's D prime. Now let's talk about criterion. A criterion is a value set by the observer depending on circumstances that only they know. Criteria vary depending on the situation. If the stimulus is above the criterion, the observer will say yes. But if the stimulus is below the criterion, then the observer will say no. And by this I mean, yes, there is something there, or no, there's nothing there. What's most important to remember is that the criterion is the bias, okay? The response biases are mindsets that people have, or tendencies to respond either yes or no. For example, if you are expecting a super important phone call, your attention is going to be on the phone, and this may result in a situation wherein you imagine the signal amidst ordinary noise. And this is where we get into different types of criterion. And these include liberal criterion, neutral criterion, and conservative criterion. Let's start with the liberal criterion. The liberal criterion is when the criterion is negative, resulting in high false alarms. So with the liberal criterion, you got the mindset of, I gotta get the phone when it rings. My mind is on the phone. The neutral criterion is where the value is near zero. So this is kind of like, if it rings, it rings. Nothing out of the ordinary. That's neutral. And then with the conservative criterion, this produces a positive value of C, and it results in a lot of misses. So your mindset with the conservative criterion is, screw that phone. I don't want to be bothered. Also, a fun fact, sensitivity, that's D prime, and criterion interact in very interesting ways, right? Sensitivity may be high. You may have a very high value of D prime. But if the criterion is relatively low, then there still may be a lot of false alarms. Because again, a negative value of C, that's a liberal criterion. Your mind is like, ooh, I gotta get the phone. And so because of that, you start hearing things, you start making more false alarms. Okay, we're gonna get more into that in just a minute, but for now, TLDR, let's go over the bias values of criterion. C. Negative ones are liberal. Positive values are conservative. And a value near zero is neutral, or unbiased. Okay, a little bit more on D prime and criterion. A D prime of 0 means that the noise and the signal sound the same. And here we see no sensitivity, which makes sense because D prime is a measure of sensitivity. And if a D prime has a value of 0, there is no sensitivity. A d prime of 1 is similar to what we would get in a threshold test, that is, absolute threshold. Fairly weak stimuli, like a hearing test. It is detectable half of the time. And again, that is a d prime of 1. With this, there is a good bit of overlap between the two curves, going back to that bell-shaped curve. Oh, but then we have a d prime of, say, 4. Okay, a value this high, you can easily detect the signal amidst the noise, because here there is a lot of space between the curves. That ringtone, okay, that is loud. That is clear as day if you have a d prime this high, because your sensitivity is way up there. You are detecting it. Yes. And to this point, d prime is a subtraction of z-scores. So the z-score of the hit minus the z-score of the false alarm gives you the d prime. And this is why we need to know the difference between the hit and the false alarm. Knowing the hit, knowing the false alarm, taking the z-scores of these, subtracting the z-score of false alarm from the z-score of the hit, this gives you d prime. If the false alarm rate and the hit rate are the same, then the d prime will be 0, because subtracting any two identical values will get you 0. Z-scores below 50%, that is, below the average, will get you a negative value, whereas z-scores above 50, right, above the average, will get you a positive value. So again, if false alarm rate and hit rate are the same, you're going to wind up with a d prime of 0. If the z-scores are below 50%, you'll get a negative value. If the z-scores are above 50%, you'll get a positive value. Ooh, but what about bias? Criterion. When it comes to liberal criterion, we see a high false alarm rate. Okay, here we have negative values of C. Conservative criterion means a high miss rate. Okay, here we have high positive values of C. Very much the opposite of the liberal criterion. And then the neutral criterion is just the unbiased middle, right? There is symmetry between the hit rate and the false alarm rate. So what would a neutral criterion look like in numbers terms? Well, this was brought up in class, and I'm going to repeat it here. A 0.8 hit rate and a 0.2 false alarm rate would show symmetry, or a 0.7 hit rate and a 0.3 false alarm rate would show symmetry. Ooh, and to this point, little fun fact here, a negative d prime could mean that the task is very difficult, or that the person may confuse the two events. So confusing the signal with the noise, or vice versa. I got my water. For any sensitivity, there is a range of possible outcomes according to signal detection theory. To simplify all the possible outcomes for a given signal strength, researchers developed a way to summarize all the possible outcomes across all possible criteria. This summary is the receiver operating characteristic curve. The ROC curve in signal detection theory is a plot of false alarms versus hits for any given sensitivity, indicating all possible outcomes for that given sensitivity. A little fun fact here, kind of a retread of what we talked about already, just put here, right? When d prime is 0, sensitivity is 0. And the perceiver cannot discriminate between signal and noise. So, as d prime increases, hits and correct rejections increase, and misses and false alarms decrease. So, if d prime were perfect, we would get only hits and correct rejections. But d prime is never perfect in the real world. The advantage of ROC curves is that they capture all aspects of signal detection theory in one graph. Sensitivity, right, d prime, is captured in the bow of the curve. The more the curve bends up to the right, the better the sensitivity. Moving along the bow captures the criterion. As you move up any one level of sensitivity, the more loosely you are setting your criterion, thus opening up the possibility of more hits, but also more false alarms. Okay, note here is that the ROC curves are important in evaluating medical decision making. So just think of radiologists, right? Radiologists want to be able to detect tumors while also minimizing false alarms. Radiologists want to have the highest values of D' that they possibly can, because then they'll be able to best distinguish real tumors from false alarms. More correct rejections, more hits, fewer false alarms, fewer misses. Let's talk about masking. Masking is just difficulty in seeing one stimulus when it is quickly replaced by a second stimulus. Masking can be done with visuals and with audio or sound, right? So multiple stimuli in sequence make it harder to detect individual ones. This is kind of like the subliminal message stuff. The term subliminal just refers to the influence of stimuli that we are not consciously aware of. Subliminal stuff relates to the topic of a threshold and to mass priming, right? We can be influenced by stimuli that we are not aware of. The term subliminal just means below the absolute threshold. Also, a little fun fact here, right? Limin means threshold, so subliminal means sub-threshold. Okay, remember, the absolute threshold is the level at which we can see something half of the time. So, by that logic, subliminal stimuli are sometimes visible to us. Sometimes we can actually see them, but only about half the time, probably less. And now there is a lot of debate as to whether stimuli that we don't see can actually influence us. One possibility is that there may be a subjective threshold that is somewhat like the absolute threshold. Now, by this definition, stimuli below the subjective threshold could influence us. But as another way of thinking about it, a D' of 0 means that the person cannot distinguish between the noise and the signal. So if we establish an objective threshold for subliminal stimuli, then it would be something like a D' of 0. Okay, we're almost done, I promise. We just got to talk about neuroimaging techniques, then touch on applications, and then we're out of here. So, neuroimaging techniques. Neuroimaging techniques are technologies that let us visually examine living human brains. These techniques allow scientists to correlate perception with brain activity. The two goals of neuroimaging are 1. To reveal where perception happens in the brain, and 2. To reveal how perception unfolds through the brain over time. And this gets us into the electroencephalography, or EEG. The EEG is all about using electrodes to measure the electrical output of the brain by recording electric current at the scalp. EEG is good for determining the overall activity of the brain. EEG tells us what happens across time, and it gives us a broad scope, but it cannot get down to detail. That is why we have the fMRI. fMRI, or functional magnetic resonance imagery, is all about magnetic fields that create a three-dimensional image that can capture both the structure and function of the brain. The fMRI is one of the most widely used imaging techniques. It gives us better detail of where something is happening. The MRI alone, just the magnetic resonance imaging, gives us structure. We still need function, F relates to the functionality, so which parts of the brain are active at any given point in time. The functional aspect, F, has to do with how cells utilize resources. Cells use more oxygen when they are active. That's why our breathing rate increases. The fMRI indirectly determines the activities and regions by looking at what happens when the blood becomes more magnetically charged as blood gets used. When the blood is being used, it becomes more magnetically charged, and the fMRI is able to then detect this magnetic charge and really get a feel for, hey, something's happening here. fMRI has very good spatial resolution. And here, a quick note, a voxel is just the region of space where we see activity in an fMRI. And because I just cannot stop talking about this, fMRI gives us good resolution of the area in the brain that we think is most active. However, we do have to be careful about drawing any strong conclusions from EEG or fMRI because the differences in activity may be extremely slim. although granted the technology has come a long way. There is another technique worth knowing, and that is transmagnetic stimulation, or TMS. TMS is a procedure in which a magnetic coil is used to electrically stimulate a specific region of the brain. Now, TMS does not record anything, okay? All this thing does is stimulate the brain. If the TMS pulses are timed properly and applied to the brain, you can prevent certain functions of the brain. Deactivating parts of the brain cues us into what sort of functions they serve, because we learn more about what function is served by a certain area of the brain when it gets shut off. So if I put the TMS device here and I disrupt whatever this part of the brain is responsible for, you'll know that something happened because maybe I won't be able to see. TMS is useful in treating depression, right? TMS can be just as effective as electroconvulsive therapy, or ECT. TMS may actually be better than electroconvulsive therapy because TMS has no nasty side effects. Research also shows that TMS can be used to treat memory loss. So memories can be restored to some extent in certain cases. And in these cases, we see long-lasting memory improvements thanks to TMS. Okay, finally, we're talking about applications of this stuff, right? So, applications of psychophysics. We have audiology, right? This is the treatment of hearing loss. Audiologists assess hearing loss and help fit people with hearing aids. If medical issues pop off, audiologists will forward patients to medical doctors who specialize in auditory issues. Also, real quick here, audiologists are just people who specialize in diagnosing hearing impairments, and it requires about 3 to 4 years of doctorate training. Ooh, fun fact. An audiological report is the result of a hearing test. I never knew that. Moving from the ears to the eyes, we have optometry. This is basically the treatment of bad eyes. An optometrist is a trained professional who specializes in diagnosing visual impairments and diseases. Optometrists utilize forced choice in their measures of visual clarity. And some not so fun facts in this field, we have myopia and presbyopia. So myopia is a condition causing an inability to focus clearly on far objects. Myopia is also known as nearsightedness. It occurs because accommodation cannot make the lens thin enough. And then with presbyopia, this is just a condition in which incoming light focuses behind the retina, leading to difficulty focusing on up-close objects. This is common in older adults when their lenses become less elastic. We did it. That's it. That is everything that I have in the notes for Chapter 2, Research Methodology. Thank you all so much for watching. This has been the second chapter of Sensation and Perception. That is Psych 323. And yeah. Till next time.